Hello everyone, my name is Sanjeev Kaushik Ramani and I'm going to present a technique for rapid establishment of transient trust for NDN based vehicular networks. This is a project that I have been working on with my advisor at School of Computing and Information Sciences in Florida International University. Our aim in this work is to explore the NDN based vehicular networks for collaborative driving applications where the vehicles can communicate and assist each other, share views from onboard cameras, or perform distributed predictions. We also wanted to explore the importance of trust in such scenarios and if we could find a way to design rapid establishment of transient trust in such networks. To give more perspective, we are interested in the collaborative benefits in a vehicle to vehicle communication, like you can see here on the slide, or a vehicle to infrastructure or communication, or a vehicle to everything or V2X communication, which has become popular with the advent of DSRC, WAVE, and other LTE based approaches. Reliable trust among such communicating vehicles is important for vehicles to trust on input or messages from each other. It is, however, seen that traditional long standing trust is not useful in such scenarios because of the short interaction times between these vehicles. However, manufacturer provided certificates provide a certain degree of trust, but it's not sufficient in all cases wherein you have a collaborative application in which these vehicles are involved and their data or action is plays a major role. We thus started off by looking and surveying the different categories of trust that can be applicable in our scenario. We see that we have two broad categories of trust, namely the static or knowledge based trust, where the communicating entities have partial or full knowledge of the other entity, which it has gained from either encounters it has had with it earlier or through a trusted third party. And the second category being dynamic or interaction based trusts, which involves the entities willing to collaborate on a common task without any prior interactions or the involvement of third parties. You can see a possible scenario, application scenario that we are trying to target, which is basically a collaborative lane change and showcases the importance of the dynamic interaction based trust. The traditional approaches like PKI, public key infrastructure model, or the web of trust model relies heavily on pre-existing configurations and are highly reliant on the existence of constant connectivity with infrastructure, which may be infeasible in a vehicular scenario owing to the mobility patterns that it follows. Also, the long-standing trust relationships we create by using these methods is not quite applicable to most vehicular applications, since vehicles are in contact only for tenths of a second or even less, and usually meet very infrequently. For our design, we consider the use of Swift Trust, which was first introduced by Meyerson and belongs to the category of a subjective model of trust management. It has since been widely used in temporary groups where heterogeneous entities work towards a common goal with tight deadlines. It's a task based approach with cognitive and normative components, which is an aggregation of opinions and behaviors that are performed within set norms. Having seen that Swift Trust can be employed in temporary groups, let us now try to understand the characteristics of such groups and if vehicular networks qualify to be a temporary group. Well, entities in such groups have limited or no prior interaction and are not entitled to meet again in most cases after a goal is achieved. The goals here are task oriented and highly diverse with very strict deadlines. Autonomously driving vehicles with collaborative goals thus perfectly fits as a temporary group, making Swift Trust highly deployable and sought after. The requirement, though, is for a secure communication design. NDN, which is built on the data centric approach with built in security primitives with all the security benefits, provides the ideal mode for vehicular communication, enhanced by adopting Swift Trust for transient trust establishment. The other advantages include named content retrieval, support for multicast communication, possibility for in-network caching and thus use of data mules in case you want better dissemination of information. All of which makes NDN the perfect match for vehicular communication. Let's now look at how we can adopt Swift Trust for vehicular networks. Let us consider two cars want to mutually trust each other. The first car starts off by performing a self test and senses the surroundings and aggregates the information it can find. It then assigns a task for a reward with some set norms uh, as a part of the normative component that we discussed. A surrounding car, on receiving the interest and by accepting to perform the task, implicitly promises uh, to perform the task with no malicious intent, so that it can maintain a good reputation in the network. The car that presented the task now compares and computes its findings to identify the trustworthiness of the other vehicle. The proximity to the correct value will provide a higher trust score. The calculation of trust depends on the cognitive and normative components on which Swift Trust highly relies. The cognitive component of trust depends on the ability, benevolence, and integrity aspects, along with the current focus and expectations of the vehicle, which is termed as self orientation. As you can see in the slide, the formula to calculate cognitive trust is the summation of the ability, benevolence, and integrity trust divided by the self orientation, which refers to the current focus of the car. The calculation of the normative component is a little complex, factoring in the risks that the participating vehicles are willing to take in order to accomplish the provided task. A special case of prisoner's dilemma, which is taken from the game theoretic approach, is used wherein a vehicle decides to perform the task if it feels it is beneficial and the benefits outweigh the personal cost that's involved in it. If the vehicle declines to perform a task that it's being offered, there is nothing that it loses or gains in that process. The other aspects that are used to collaborate include the temptation for the vehicle to collaborate, which should outweigh the reward on completion of the task. The reward it's entitled for on completion of the task, which in turn should outweigh the punishment it would receive in case the vehicle does not perform the task well and doesn't meet the outcome that was expected. And finally, you have S, which in the slide, which refers to no loss or no gain. The formula thus is as shown in the slide, with the total transient trust involving the cognitive and the normative components, both of which were calculated based on our discussion in the previous two slides. The tasks that are used and provided and posed by the vehicles are usually spatiotemporal or involving some kind of a processing capability uh, of the vehicles. A spatiotemporal task is as shown in this slide, wherein the vehicle would like the participating vehicle to provide the distance of the nearest roadside unit. You can see the interest and data messages that are being exchanged and the NDN naming convention being used in order to make this communication feasible and possible. And the second example that we would like to discuss is a visual matching task, which basically involves more of a processing capability of the vehicle. Here, uh, the vehicle that wants to check for the trustworthiness of the other vehicle asks the second vehicle to perform a visual match of a signboard and check if the speed limit is specific to the number that it specifies. And based on the results that it receives from the other vehicle, it would be able to perform the uh, calculation of the trust score based on the cognitive and normative components we discussed and come up with the score for the other vehicle, which is car B in our case. There are, however, some certain security and privacy concerns that arise when trying to perform this activity. You can have denial of service, wherein malicious vehicles could send multiple queries just to spam the network and make the network break down, limiting the number of outgoing interests to a threshold can to some extent alleviate this challenge or concern. You can also have replay attack, wherein every vehicle can assume multiple roles and they can start replaying packets that they have received from different vehicles. However, usage of timestamps nonces can help in identifying the freshness and authenticity of the packets or the messages that are being exchanged. Other security and privacy concerns could be collusion, wherein multiple vehicles with malicious intent can join hands in trying to perform tasks and try to break the network. A simple example could be vehicles trying to falsify information just to gain access to the network or be a part of a collaborative task. There could also be cheating with sensor information in terms of fake data injection, wherein attackers try to alter the perceived position, speed, direction, etc., in order to falsify information. Colluding attacks, also called clone attacks, are uh, hamper the trust score of the vehicle in the network. The other security and privacy concern is ID disclosure, which still needs to be addressed. In summary, trust is an integral part of any communication, and it is more pronounced in a temporary group like Vehicular network. In the paper, we described the use of deploying a swift trust-based approach along with the benefits of NDN communication for rapid transient trust establishment. With this, I would like to thank all of you for your attention and open the floor for any questions. Thank you.